Good morning, students. I am Y.S. Chandrasekharaya, Associate Professor of Physics, Government First Grade College, Tumkur. So, this is my third session. So, in this session, I will going to discuss the relation between elastic constants. Now, you have already understood that which are the elastic constants. So, we will come across four elastic constants, out of which three I have already explained. So, that is Young's modulus, rigidity modulus, bulk modulus. So in addition to that, we have one more elastic constant, that is Poisson ratio. So it can be defined as the ratio of lateral strain to its longitudinal strain. It is lateral contraction to its longitudinal elongation. So this is how we can define the Poisson ratio. Poisson ratio is always represented by the letter sigma. So with the help of this this knowledge, so I will going to derive the relation between elastic constants. In order to derive the relation between elastic constants, we have to consider the diagram of a cube. So let the three forces which are acting on the cube are F1, F2 and F3 are acting perpendicular to the three faces of the cube ABCD, ADHE and ABFE of a cube. The face of the cube is represented as A, B, C, D, E, F, G, H of unit length. So each force produces an extension in its own direction and a compression along the other two perpendicular directions. Let alpha be the elongation per unit stress and beta be the contraction per unit length per unit stress. Thus, the elongation along the direction of the force F1 will be represented as alpha into F1 and the contraction along the remaining two directions due to the force F1 is given by beta into F2 and beta into F3, where alpha represents the elongation and beta represents the compression. So then let the three forces are simultaneously acting on the faces of the cube. Net elongation along the direction of the force F1 is equal to A, that will be equal to alpha into F1 minus beta into F2 minus beta into F3. So now, why I have written this with a negative sign? Contraction or the compression's values are written with a negative sign because when compared to the elongation, the contraction value is always less. That is the reason why. So these two forces carries with a negative sign. So the net elongation along the direction of the force F2 is equal to, it is represented as B, that will be equal to alpha into F2 minus beta into F1 minus beta into F3. So similarly, the net elongation along the direction of the force F3, it is represented as C, that will be equal to alpha into F3 minus beta into F1 minus beta into F2. So three elastic constants, namely Q, N, K, and can be expressed in terms of alpha and beta. Can be expressed in terms of alpha and beta. So, case number 1. Suppose only the force F1 acts and other forces will be equal to 0. F2 and F3 is equal to 0. So, then we have the case of longitudinal stress. The longitudinal strain is represented by alpha into F1. Longitudinal stress is nothing but F1. So, then we can define the Young's modulus in this way, that is longitudinal stress by longitudinal strain, that is Q is equal to F1 divided by alpha into F1, where F1 gets cancelled. So you will be left with Q is equal to 1 by alpha, where Q is the Young's modulus and alpha is the elongation value. So you call this as equation number 1. So case number 2, suppose the force F3 is equal to 0 and F1 is equal to minus F2. The elongation along the direction of the force F1 will be equal to A, that will be equal to alpha into F1 minus beta into minus of F1 plus 0. So then F1 is equal to A, that will be equal to alpha plus beta into F1. So shearing strain can be represented as shearing angle theta is equal to twice the value of A, that will be equal to 2 into alpha plus beta into F1. Therefore, rigidity modulus can be defined in this way. It is defined as the ratio of shearing stress divided by shearing strain. So that here we know the value of stress as well as strain. So this stress value is represented as N is equal to F1 divided by shearing strain we have already determined. So that is given by 2F1 into alpha plus beta. So therefore, the rigidity modulus N can be written as 1 over 2 into alpha plus beta. You call this as equation number 2. So case number 3, let F1 equals F2 equals F3. So that means to say all the three forces acting on the faces of the cube are equal. So now the body is subjected to uniform stress in all the directions. So then the elongation along the direction of F1 is equal, A is equal to alpha into F1 minus 2 beta into F1. So if we take, if we simplify this above equation, you will get A will be equal to alpha minus 2 beta into F1. So this gives the increase in volume. So increase in volume is given by 3 times the value of A, that will be equal to 3 into alpha minus 2 beta into F1. Therefore, volume strain is represented as 3 into alpha minus 2 beta into F1. So therefore, bulk modulus is equal to normal stress or the volume stress divided by volume strain. Now we know both the values. Volume stress is nothing but F1 and the volume strain is nothing but 3 into alpha minus 2 beta into F1. If you further simplify this by making some simplifications, you will get K is equal to 1 by 3 into alpha minus 2 beta. You call this as equation number 3. So then I will now going to derive the relation between Q, N and K. So from using equation 2, we can write 2 into alpha plus beta is equal to 1 by N. It is as good as 2 alpha plus 2 beta is equal to 1 by N. So from the relation 3, we can write alpha minus 2 beta is equal to 1 by 3K. So 3 alpha can be written as, by adding above two equations, we can write 3 alpha as 1 by N1 plus 1 by 3K. So alpha can be written as 3K plus N divided by 9Nk. So from the relation 1, we can write Q is equal to 1 over alpha. It is as good as alpha is equal to 1 by Q. By cross multiplication, you will get this equation. So then Q is equal to 9Nk divided by 3K plus N. You call this as equation number as 4. So with this, I will close my session, third session. Thank you.